1 in 3 adults is obese, not just overweight, but obese. And that by the year 2030, which is sometime in the distant future, right? 8 years from now, that it'll be 50%. 50% of adults in North America obese.
Welcome back to the show, Dr. David Perlmutter. It's so great to have you here again.
So great to be with you, Stephanie. Good to see you again.
Yes, and today we are discussing your new book, Drop Acid. And I have to say that all of your books, the titles of all of your books are just like top shelf clever. You know, you have Grain Brain, Brainwash, and now Drop Acid, which you might think is about psychedelic therapy. And of course it is not. We're talking about uric acid today, but I wanted to tell you, like, really well done on all of the acronyms and all of the titles.
Thank you. I appreciate that.
All right. So as I mentioned, we're going to be talking about uric acid today. And I was saying this to you a little bit in the pre-chat as by way of background, starting with maybe understanding some of the mechanisms at play in terms of where uric acid comes from. I think for most people, if they do recognize uric acid, they might associate it with gout, which is, of course, notoriously famous for, attacking the proximal joint of the first metatarsal, like the bunion of the big toe. So maybe we can start with gout. What are some of the observations that have been around the etiology of gout, and then we can talk about purines and fructose, et cetera, as well.
Sure. So we've, in our training and years ago, we all talked about uric acid in the context of gout, and that was your grandfather's uric acid, right? That's old school. And not that that's not important, it is, but the big new exciting news about uric acid is that, well, let me give you the title of an interesting report that came out from Japanese researchers, Uric Acid in Metabolic Syndrome, from Innocent Bystander to Central Player. And that really encapsulates what the whole book is about, and that is that this uric acid in our bodies, when it is elevated, is a powerful instigator of metabolic mayhem, meaning that it's now been identified as not just being elevated along with high blood pressure and increasing body fat, increasing blood sugar, but it's causing it. It's playing a mechanistic role, that this uric acid is a danger signal to the body saying, winter's coming. We need to make fat. We need to raise the blood pressure so we're protected against becoming dehydrated. We need to raise the blood sugar so that we can power the brain, so maybe we can find food and avoid being eaten by another animal. So this is a mechanism that's been present in humans and even in our primate ancestors for millions of years. The fact that we have much higher uric acid levels than other mammals. It's a danger signal, and it's a survival mechanism in the presence of not having enough food. But now, obviously, that's not the case. And the huge triggers for uric acid that are telling our bodies make more fat and lock it up are things like fructose, fruit sugar, alcohol, and purines that you mentioned that have long been associated with another problem related to elevated uric acid, which is gout. But those very same purines, because they raise uric acid, are associated when the uric acid is elevated with things like high blood pressure, elevated blood sugar, increased body mass index, increasing our body fat, and locking it up as well. So it's not only exciting for me because it now answers so many questions, but it also offers up a really powerful new tool in the toolbox to help people who are doing the best they can, but can't seem to lose that weight, can't seem to get that final blood sugar level back to where they want it, are still fully dependent on blood pressure medication. I'm not saying that getting your uric acid level under control is going to be the end all, but it's certainly a powerful tool just to take, to really reach that goal in so many people. And when I mentioned a moment ago that it fills in the blanks, or it's this missing piece of the puzzle, we've known, for example, since 1970 in the journal The Lancet, that fructose consumption, when increased, as it is now, is associated with all those metabolic issues and more: elevated triglycerides, dyslipidemia, high blood pressure, higher blood sugar, increased body fat. But we didn't know how it happened. We didn't know how and why it happened. Now we know, because elevated fructose turns on the production of uric acid. That's its end of the line metabolite. That's what it becomes. And that uric acid's telling the body, winter is coming. We need to store fat. We need to raise the blood sugar. So it really answered a lot of questions for us. And it's very exciting because, as you and I will talk about later on, getting uric acid under control is not that difficult. It's actually very straightforward.
It's incredible. So for the listener who may not be familiar with some of the constituents of gout, let's talk about what a purine is. So what are purines?
Purines are the normal breakdown product of the DNA and the RNA that's found in foods. Foods that are higher in these purines, or providing purines, are foods that are much denser in terms of their cellularity, more cells, more tightly packed, and therefore there's more DNA and RNA in these cells. So certain foods, for example, like organ meats, like liver and kidney and game, venison, for example, shellfish like mussels and scallops, and even, truthfully, certain vegetables. Although the meat-related purines can raise uric acid, it's been demonstrated that you can consume high purine vegetables, like, for example, the cruciferous vegetables, and it is associated actually with a lowering of the uric acid because of some offsets that those vegetables provide, like dietary fiber, like certain bioflavonoids like quercetin that actually leads to lowering of the uric acid. We'll definitely want to look at quercetin a little bit later on. We talk about nutritional supplements. But the truth on the purines is that 2/3 of the purines circulating in your body are actually made from the breakdown of your own tissue. When you exercise, for example, break down muscle tissue, you are liberating a lot of purines into your system. It turns out that it's interesting, and as part of a diet to lower uric acid, it's something to be considering, as is alcohol as well. And we'll talk about the types of alcohol in just a moment. But the biggest player by far and away is the fructose consumption that is so pervasive amongst humans now. You know, the average uric acid in North America was about 3.5 in the 1920s. Now it's 6. And it has paralleled in lockstep our ever-increasing consumption of sugar. So, you know, the average American, I suspect it's the same in Canada, consumes somewhere north of 50 pounds of sugar each year. That's 5 10-pound bowling balls of sugar every single year. And now, you know, we've known that's not a good thing. But we've been focusing for a long time on the fact that it's a glucose load, right? Because table sugar, sucrose, is 50% glucose and 50% fructose. So we really focused on the glucose. Why? Because it's that glucose that stimulates the insulin production. Therefore, high levels of glucose, higher levels of insulin, we become insulin resistant. We develop insulin resistance because we have so much glucose floating around. Next thing you know, we're a diabetic. And we've said, I don't know if we've said it, but it's been said over the years that, well, fructose, because it doesn't use insulin for its metabolism, might be a safer choice. Therefore, let's go all in on the high fructose corn syrup, etc. Well, it turns out that fructose indeed is related to the production of insulin resistance and raises blood sugar, blood glucose. So it's anything but a safer sugar. It's in fact even more threatening because it's not just blood sugar that it targets. It also increases blood pressure, and it also directly leads to what we call lipogenesis, the creation of body fat. And, you know, for most people, that's not necessarily what they want to do. So we know now that in North America, more than 60% of the packaged foods in the grocery store have added sweetener. And by and large, these are either high fructose corn syrup or derivatives of high fructose corn syrup having lots and lots of fructose because it's cheaper and it's sweeter than glucose. So we're really favoring more and more the addition of fructose to our foods and watching these skyrocketing rates of obesity, of hypertension, and certainly diabetes. We know that here in America, there are close to 80 million pre-diabetics and about 34 million already diabetics. So this is about 45% of adults here in America. I'm certain it's the same in Canada or close. That we're talking about 45% are either diabetic or pre-diabetic. We know that 88% of American adults has at least one component of what we call the metabolic syndrome. And that means that only about 1 in 8 adults here is metabolically intact. And I submit that fructose is the biggest player. And now we understand why. It's through this alarm system called uric acid, raising the alarm that winter's coming, make the body fat, raise the blood pressure. So when we target that uric acid and bring it under control, by lowering our fructose consumption, for example, increasing our vitamin C, taking nutritional supplements that help to lower uric acid, it's a huge leap forward.
So let's talk about the metabolism of fructose and how it is mechanistically different from glucose. One of the things, listeners of this podcast for many years will know, glucose, it's the molecule of life, as Dr. Robert Lustig on our show has said. We take glucose into the cell and we create ATP from it through, the tricarboxylic acid cycle. But fructose is different, even though it is the same, it doesn't have the exact same structure. They're both carbon rings, but there's just one little difference on the fructose chain that makes it very different in terms of its metabolism. So let's talk about how fructose, instead of being a substrate for energy production, is actually one of the ways that we deplete our cells of energy, or ATP.
That's right. And interestingly, the way that fructose is metabolized is the identical pathway by which we metabolize alcohol. And what your friend Dr. Robert Lustig has said is that fructose is alcohol without the buzz. And I love that because it offers us up nothing. I mean, our nutritional requirement of fructose is 0, and yet, look what's happening now. But you quite correctly identify glucose as the molecule for energy production, because it does allow, through the Krebs cycle, the production and glycolysis as well, the production of these ATP molecules, whereas fructose is the molecule of energy storage, getting ready for use of energy in the future. And while their chemical formula is exactly the same, they are structurally different, and they are as different as night and day. It's unfortunate that, it's, fructose sugar, lactose sugar, glucose sugar, they're all sugars. We sort of look at them, we study them on the same day in biochemistry class, but they are so different. And glucose metabolism is an energy producing, it's something that allows us to metabolize, whereas the production of energy storage is what happens when fructose is metabolized, whereas glucose produces these ATP, currency of energy molecules. Fructose actually takes ATP and reduces it down to AMP, and therefore depletes intracellular phosphate. And that is a huge event. That change from ATP to AMP, adenosine triphosphate down to adenosine monophosphate, that depletion of this intracellular phosphate, signals our bodies to prepare for winter. It changes our entire metabolism away from energy utilization to energy storage. And it is what happens, for example, in a bear. If a bear is as bears prepare to hibernate, they turn off a certain pathway that's called AMP kinase, which would otherwise keep that bear lean and mean, fighting machine. And it shifts that metabolism over to AMP deaminase. And what AMP deaminase does is it says, raise the blood sugar become insulin resistant and make a lot of fat. And that's what the bear is doing by eating fructose left, right, and center. 10, 20 pounds of berries in a single day to get ready to store that fat so that he or she can survive during the time of hibernation. Then during hibernation, the animal is tapping into its energy resource, which is the body fat, and using that energy resource as a caloric depot, and also, interestingly, as a source of metabolic water. When the bear or you or I burn fat, we're creating water in our bodies. So this body fat that it stores is not just a calorie resource, but it's a resource to make metabolic water, because it doesn't eat all winter when it's hibernating, nor does it drink. And it explains why, for example, the camel, I love this example, it's walking across the desert for weeks at a time and doesn't drink any water. Why? Because what is the most identifying characteristic of the camel? The hump. What's inside the hump? It's not water, it's fat. So it has a resource for energy. It has a resource to make what's called metabolic water, like whales do, like the hummingbird does. The hummingbird, when it's getting ready to fly from where you live to where I live, is 40% body weight fat. And that's its resource, not just for calories to make the epic journey, but for water as well, metabolic water. And if you want hummingbirds in your backyard, what do you put out there? You put out sugar water. It's fructose that tells that hummingbird, get ready for your epic journey. Same thing happens in your body and my body and in the body of everybody on the planet. And that is that we are very parsimonious or thrifty as it relates to the calories that we consume, specifically those signaling calories, which are the sugars and specifically fructose. Our Paleolithic and even our primate ancestors would eat these berries and other fruits in the late summer and in the early fall because they were sweet. And that's why we like sweet to this day. There's nobody who will tell you, no, I don't like sweets. We choose not to eat them because we know they're bad for us, right? But we like them. So we all have that sweet tooth cooking in the background, but we're bringing on our prefrontal cortex saying, yeah, I really want to eat those sweets, but I know it's not good for me. Would I like to drink a Coke? I would. I absolutely would put a Coke, drink a Coke, pour it over ice, have a straw. That would taste, I would still probably enjoy that, or a Dr. Pepper, one of my favorites. But yet, that's my amygdala brain saying, sweet, seek it out for survival. That's going to help you live. My more adult in the room part of the brain is saying, yeah, but you don't want to do that, do you? You know what that's going to do to your insulin levels, what it's going to do to your fatty liver, increasing that, and all the stuff. So we override these primal instincts. Those primal instincts allowed us to survive because sweet prepared us for winter. Sweet identified fruits as being safe. There aren't any fruits that are sweet that are harmful for us. They're not, there's no poisonous sweet out there. So we refined our genome and our brain wiring to give us this desire for sweet and the little dopamine rush that we get when we eat it. But nowadays, hopefully, we are able to bring on board our prefrontal cortex and override the amygdala and make better choices. Getting back to a conversation you and I had last time I was on your program. So it's a very interesting story. And I have to tell you that my interest in this evolutionary environmental mismatch, that's what our problem is now, that we've evolved with this desire for sweet and this ability to make fat when we eat that sweet in a different environment of food scarcity, an environment in which we might be threatened as well. When we were hungry, not only could we not find food, but we might be eaten by an animal that notices that we're kind of staggering around, can't make good decisions because our brain isn't powered. We evolved these mechanisms to make sugar to power our brain. So we have this evolutionary environmental mismatch today where our environment is giving us all this fructose. We don't need to do much in our physical world. We don't have to sleep very much, or we choose not to, rather. So this evolutionary environmental mismatch has been something I've been interested in for more than half a century. I wrote my first article about this, published it in 1971 when I was 16 years old in the Miami Herald. And I asked the question, what about us who are living today with this outdated machinery? That was my conclusion, because we're not going to evolve quickly enough to be able to tolerate the fructose, the sodium. We'll get to that. The high level of purines in our diets, and certainly the alcohol that we are consuming.
You bring up I want to come back to AMPD and AMPK in a minute, but just talking from our ancestors, in the book you talk about this. I believe it was apes who developed this, or there was an environmental selection for apes that had this enzyme fructokinase, and that's essentially the apes that ended, or I guess they were in the Homo sapien lineage, let's say, and they ended up sort of seeding, who you and I are, and the current evolution of Homo sapiens are. Can you talk a little bit about what that evolutionary selection was? And it's pairing up perfectly with what you're talking about in terms of this modern evolutionary mismatch. In terms of now, we don't necessarily ever worry about famine. We don't ever worry about having to hunt and not knowing when the next kill is going to come, etc. Can you speak to this evolutionary selective bias around fructokinase?
It's really just it's just a breathtaking story, because and I'll recount that in just a moment. But for me, it's been so exciting, because in everything I do professionally right now, as it relates to clinical work or looking at metabolism, et cetera, I always ask myself now, and I didn't do this so much before, why might this have been an advantage in the past? And for example, we talk about you're at increased risk for Alzheimer's if you carry the APOE4 allele. And so that's a bad thing. Why would you want to have that? Why would you want to have this uricase mutation so you have a higher uric acid? Why would you want to, have foreign body fat from fructose? Those are obviously bad. Why would I be saying that, for example, insulin resistance might be a good thing? Because it's in the context of now versus then. Because back then, APOE4 allele increased inflammation, which was protective. Because back then, having this uricase mutation made ultimately more body fat and allowed us to survive. So between 14 and 17 million years ago, a long time ago, during what is called the Middle Miocene period, the Earth cooled over 1 million years. So it's not something that happened very quickly. So it's an environmental pressure, but it's a very slow acting one. And as the Earth cooled, less food was available for our primate ancestors. So they had to do more with less. And one of the mutations that happened, actually it was a series of mutations, happened in what is called the uricase gene, the gene or suite of genes that is involved in the making in the body of an enzyme called uricase. Uric as in uric acid, case as in it breaks it down. So we lost, or our primate ancestors lost, over 1 million years the ability to make this enzyme uricase, and as such, our uric acid levels over time increased more and more. Now, this gave a slight advantage to those primates who had these mutations and had lost their uricase, therefore their uric acid levels went up. That elevated uric acid gave them a superpower. And what was that superpower? More body fat. So they're the ones who survived and were able to pass on their genetic material, that uricase mutation, as opposed to those who didn't have it. We inherited that. We don't have in our bodies uricase. We don't break down uric acid using uricase. So our uric acid levels are 4 to 5 times higher than other mammals, for example. And it was a survival mechanism until very recently. Even our Paleolithic ancestors, even just before the onset of agriculture, when was that? 14 to 17,000 years ago, we were basically hunting and gathering, and having that advantage of being able to make a little bit more body fat was even advantageous back then. Today, it's not that way. Now we're targeting that physiology to make us fatter. That same mechanism that allowed our survival for millions of years, if you include our primate ancestors, is now directly responsible for the number one cause today of death on planet Earth. It is not an infectious viral agent. The number one cause of death today, according to the World Health Organization, are the chronic degenerative conditions like Alzheimer's, coronary artery disease, type 2 diabetes, and even some forms of cancer. And the relationship is really quite complete. A study that was published, a collaborative study in Japan, looking at 90,000 people, 42,000 men, 48,000 women, followed them for 8 years. And what did they find? They only looked at one thing at the beginning of the study. What is your uric acid level? And then they followed this huge group of people for 8 years. Those who had the highest uric acid level, above 7, had a 16% increased risk of what is called all-cause mortality. It basically means dying of anything. They had a 39% increased risk of cardiovascular death, basically a heart attack. They had a 35% increased risk of dying, stroke. So this is pretty profound, talking about cardiometabolic types of issues. And I find really quite compelling the fact that for every point elevation above 7, there was an 8 to 13% increased risk of death, again, from all causes. So every point increased that risk of death even further. That's a pretty profound relationship. And I think it really helps solidify our understanding of the mechanism, and which we know, but why it's really important. We're out there fighting to survive. Face it, now longevity is declining in North America, and that happened before COVID. That we reached the top, and now we're starting to lose ground. And without question, it's because of the aggressive changes to our metabolism that we are inducing in ourselves by signaling this and certainly other mechanisms as well.
So would you say then that uric acid, would that be a reasonable proxy that might indirectly tell us what our fructose consumption would look like? In the same way that we might look in glucose, we might look at an HbA1c, let's say, to look at the average 3 months of glycated end products. Would uric acid levels be, is uric acid, let's say, an HbA1c equivalent for fructose?
I would say that after you get the baseline, it would be. So the hemoglobin A1C is standardized, right? So we know what so-called normal levels are and what abnormal levels are. But I would say as it relates to the individual, you would first need to get a baseline and then follow fructose consumption and see what the changes are. But yes, and one other thing I'll say about fructose that's really, I think, very important is it is, like glucose, a highly glycating, or in this case, it binds to proteins in a very similar way. In fact, more aggressively than glucose does, and therefore leads to those issues with protein like increased oxidative stress, increased inflammation. So in and of itself, even before you get to the uric acid, which is a powerful increasing event as it relates to inflammation and oxidative stress itself. Not to mention, and now I'll mention, why do people say not to mention? Then they mention it, right? Not to mention, but I will mention actually, or it goes without saying, and now I'll say it, that, very important thing that uric acid does uniquely after it has been formed from fructose primarily, but also alcohol and purines, is it inhibits nitric oxide. And why should we care? Because nitric oxide, we know, is important as it relates to the dilatation or the opening up of blood vessels, that something we need to get blood to our organs, like the brain and the heart and the kidney, et cetera. And that when nitric oxide is not working effectively, the blood vessels can't relax and therefore the blood pressure goes up. That's how uric acid keeps the blood pressure up, for example, in our ancestors when they were dehydrated and couldn't find water. That was the upside of it. It also explains why high uric acid is strongly correlated with erectile dysfunction. And here's another aspect of nitric oxide that's not well known, but really actually very important. Nitric oxide in the blood vessel is fundamentally important to allow insulin to make its way through the lining of the blood vessel and then into the cell, or to bind to the cell and then allow that cell to take in glucose. So there's a direct relationship then between how insulin is able to do its job and uric acid via this nitric oxide connection. So, and again, in the context of why was that a good thing? Because it was good to become insulin resistant in the day when, our only high carb, the best thing we had, we're not the strongest, fastest animal in the forest, but maybe we were clever, or, maybe we were the smartest. These days you kind of wonder, but that was the thing that kept us from being eaten by other animals and gave us the superpower to maybe find food when things were scarce. So it's always been in our interest to power the brain. We have a default mechanism available to us when we're starving that we can power the brain with fat via ketones. But having said that, the brain does really well on glucose quickly, and its functionality is something that needs to be preserved at all costs to keep us alive.
So let's come back to uric acid, and then I want to talk just a little bit about this AMPD versus AMPK pathway, because I think this will really drive it home for our listeners. So when we're consuming fructose, let's say, or the more sugar that you consume, the higher that your serum uric acid levels are going to be. So the more risk you have for gout and insulin resistance and all the things that we've been talking about. And and you can correct me here if I misspeak, but fructose, when it enters, let's say, the liver, which is where it's primarily metabolized, we have to take a phosphate from somewhere, right? And it's going to be from ATP, spoiler alert, in order to start that metabolic process. So we steal essentially this phosphate group from ATP, and we go through this again until we get to AMP. And then we have this scavenger enzyme, let's call it, AMP, like adenosine deaminase, so this AMPD. And there's almost like at this point where you're at AMP, or maybe one more step, but just for the sake of simplicity, we have AMP, and then there's this fork in the road, let's say. So you can almost go down the AMPK kinase, the AMPK pathway, or the AMPD pathway. What is the determining factor that determines whether or not we go into burning fat with AMPK or storing fat with AMPD? This is really part of the, for me, excitement. I think perhaps for you, the excitement is to finally understand this stuff, right? It now makes so much sense that, your body has to have a way of determining, is it feast or famine? Do I have enough food, or do I need to start storing food because, boy, I might get into trouble? And this switch between AMP deaminase and AMP kinase is the determinant of that. When AMP kinase is active, hey, the body thinks the hunting is good. So it says, we don't need to store fat. We can burn fat, and we don't need to make glucose because the hunting is good. We've got plenty of fuel. And that's pretty much what we all want to keep active. We want to keep our AMP kinase active all the time. And one of the most potent ways of activating AMP kinase is to exercise. That's what, dramatically turns on. It's one of the reasons we exercise. It helps keep our blood sugars down. In fact, that's where the drug metformin used in diabetes works. Because when you activate AMP kinase, you turn off a process called gluconeogenesis, meaning the new production of glucose in your body. That's shut off when AMP kinase is activated because we don't need it. The hunting is good. On the other hand, the other pathway is valuable too. We say we don't like that because we're making body fat and raising the blood sugar and blood pressure, all those things. But the reality is, take a step back, and in the context of history, powerful survival mechanism. But nowadays, we don't want to be activating a pathway in our bodies that's making body fat and locking it up so we have no access to it. We want to stay with AMP kinase. So the question is,
what is the switch? What turns on AMP kinase or turns it off? And there are two very important processes. The first is the sense of the drop of the intracellular phosphate. It's the metabolism of fructose. Suddenly we're metabolizing fructose. That intracellular AMP is formed from ATP, that drop in the intracellular phosphate that says, hey, winter's coming, make it happen, shift to AMP deaminase, make fat, store fat, because you're going to need it if you're going to survive. Then the product of fructose metabolism is uric acid, and that does the same thing. So it's just in case it didn't happen to enough great extent, we're going to let the uric acid amplify that process even further, because the uric acid is this really fundamental alarm system. So we have two ways of really keeping that switch over to make fat, store fat, raise blood sugar, and raise blood pressure, just to be on the safe side. So we see a lot of that. Uric acid even feeds back to an enzyme called fructokinase. Fructokinase is that first enzyme in the metabolism of fructose that does what? Further consumes ATP, further locks us into this AMP deaminase part of the flow chart, and tells us that it's doing everything it can to allow us to survive in the times of food scarcity. So, unlike so many pathways in physiology that at the end of the pathway, it'll feed back to turn it off, right? That's how it works. For example, if our blood sugar shoots up, then we make insulin. Insulin helps us then to bring homeostasis into play and lowers our blood sugar. And then the insulin level has a homeostatic mechanism that lets it lower itself as well. But that's not the case here. This is what we call a feed-forward process, where once you started, it tends to amplify itself as a survival mechanism. So the story even becomes more complex when but exciting. I guess I'll get excited about this stuff. When we realize that it's not just the fructose we consume, but we can do things in our bodies to actually amplify our own production endogenously of fructose as a survival mechanism, such that even if we couldn't find fructose when we're hunting and gathering and turn on the mechanisms to make fat, we still have mechanisms whereby we can make fructose in our bodies and still then increase our uric acid, make more body fat, and survive. And that's pretty exciting, because some of the things that turn that process on, this so-called polyol pathway, converting glucose into fructose, are things that we do every day, like eating a lot of salt, sitting down, eating a bag of salted chips to watch the playoffs. That raises our blood sodium level, and that turns on this polyol pathway that says, oh, we're dehydrated. Why would that make us think we're dehydrated? Because our sodium is going up. That's what happens when we get dehydrated. Well, our bodies sense that and turn on the production of fructose, because fructose can help us, when it's metabolized, make body fat. Well, what role does that have to play with respect to dehydration? Remember, body fat produces metabolic water. And that's why eating a salty meal increases our body fat, so that our bodies don't dehydrate as readily. We make metabolic water from body fat.
This is like the super geeky part that I get so excited about, because in your book, you were talking about how uric acid can directly influence hypertension, so high blood pressure. You've already mentioned the oxidative stress, which constricts the blood vessels and influencing NO. But now we're kind of moving into this salt story. And the prevailing thought is that, too much salt elevates your blood pressure. And the advice is to sort of restrict the amount of salt intake. But it's really, it's the amount of salt. It's not the amount of salt that you're taking in, but it's the salt concentration, like the osmolarity, if you will, of like how, if you just had a pretzel versus maybe you had some salt water, which is I take electrolytes and it's salty, and because I tend to eat a ketogenic style diet, those two they're very different pictures. And I wondered if you could expand a little bit on that.
That's right. And very well said. So what the research demonstrated in humans was that giving a sodium load will raise serum sodium and trigger this entire mechanism, as opposed to giving the exact same amount of sodium, but with added water, and basically to dilute it out. So it is exactly related to serum osmolarity, as you well characterize. And it can be overridden by simply consuming a lot of water. So, using an electrolyte product if you're exercising aggressively, or another time would be on a ketogenic diet where you're losing electrolytes or diluting them out, and to supplement yourself with a low level of extra sodium along with potassium, magnesium makes good sense. But, when those products are used, they're used diluted in water. And that's exactly what you're referring to.
So let's talk about why salt, and you may have mentioned it, but I just want to double click on this, that when you are when you're increasing the salt concentration, so you're increasing salt in the absence of increasing your water intake, how does this increase fructose production? Well, as you drink some water.
As
you're watching
you
this on
made me
YouTube.
do that. It was a prop. So the real specifics are as follows. What happens as serum sodium goes up is we stimulate activation of an enzyme called aldose reductase. And what aldose reductase is involved in is the conversion of blood sugar, glucose, into fructose. So that's the specifics. And in fact, it's a little bit more complicated than that. There is an intermediate called sorbitol. Actually, that's kind of an interesting thing, and that then is produced produces sorbitol hydroxylates, which then goes on to form the fructose. The only reason I mention that, so it's a little bit more complicated, but the main sensing enzyme here that gets the whole thing underway is this aldose reductase enzyme activation, as brought on by elevation of the serum sodium, brought on by hypoxia, for example. We'll talk about that in just a moment because it's actually very interesting. So those two things turn on the body's production of fructose as a survival mechanism. The only reason I broke it down a little bit more, I haven't done this before, but I just think it's valuable because this sorbitol intermediate between glucose and fructose is interesting, because sorbitol is actually used as a so-called artificial sweetener, right? You see it on packages. And why would you want to give the precursor to fructose, which we readily metabolize, into fructose? Doesn't make sense. The reason it got the go-ahead is nobody understood this stuff before. So just a take-home little nugget there is, don't use sorbitol as an artificial sweetener, because it becomes fructose, which then fans the flames of this entire process. So I did mention hypoxia. And interestingly, I'm not talking about climbing K2 here. I'm talking about the notion of becoming hypoxic, for example, because you have sleep apnea. So many people don't realize it, but during the course of their sleeping, their saturations, their amount of oxygen carried in the blood, called saturation, may decline. And it may be a significant decline, and even a subtle decline of blood oxygenation at any time, but in this case during sleep, activates this aldose reductase enzyme and begins this process of converting your blood sugar into fructose. Not that it drops your blood sugar to any significant degree, but it raises the fructose in your body, which does what? Increases fat production. And by and large, one of the biggest issues for this sleep apnea in the first place is being overweight. So being overweight, having a big belly, it tends to lead to sleep apnea. There are other causes, of course. And then that does what? Increases your body fat production. So it explains a lot. It explains to me this relationship that we've seen and we've known about for many years between sleep apnea and risk for diabetes, and risk for hypertension, and risk for Alzheimer's and coronary artery disease, metabolic issues now brought on by simply being hypoxic. Well, what was the mechanism? Well, we didn't really know, but we saw that there was a relationship. But now we know that it may well be through this activation of fructose production and increased inflammation and lipogenesis via increase in uric acid. So uric acid's the player. When we see now a very powerful study that demonstrated that if you're admitted to the hospital because you are suffering from COVID, that if at the time of your admission, they noticed that, or they in the study that you had a high uric acid level, that you triple your risk of entering the ICU, being put on a ventilator, and even of death. So this elevation of uric acid profoundly enhances inflammation. And inflammation really gets people in trouble, COVID related. It's this cytokine storm that people are now aware of, this overwhelming big storm of inflammatory chemicals, and uric acid increases the production of these inflammatory markers, these cytokines. And it doesn't have to be necessarily a storm to cause a problem. We know in one study that looked at individuals over 12-year period of time and did a cognitive assessment every 2 years, it found that those people who originally, at the beginning of the 12-year study, 1,600 people, that those who had a uric acid level greater than 7 milligrams per deciliter had a 80% increased risk of dementia, a 55% increased risk of specifically Alzheimer's dementia, and a 166% increased risk of what is called mixed dementia or vascular dementia in relationship to having a high uric acid. How does that segue with my previous conversation about cytokines? Because we need to begin talking not about cytokine storm, that's important, but what is called cytokine drizzle. In other words, this low level of increase in inflammation over a long period of time. Yeah, you can have a tsunami that takes away a landmass. That's the cytokine storm. But you can also have a little river that flows very slowly over time. The next thing you know, if you play it out over a long period of time, you get the Grand Canyon. So either a big force acting quickly, the cytokine storm, or a smaller force acting over a much longer time, decades. That's what we see. For example, in Alzheimer's, it's this slow, progressive increase in inflammation over time. That's not really alarming acutely, but ultimately damages tissues and causes things like coronary artery disease, an inflammation of the lining of the arteries going to the heart, or Alzheimer's, which is an inflammatory issue of the brain. And now that we know that uric acid is playing a role, it's really important to know what your level is. And if it's elevated, for our discussion, anything over 5.5 milligrams per deciliter, you better pay attention to that. And getting it lowered is not that difficult. And checking it at home is not that difficult. You can go online and buy a uric acid monitor, just like you check your own blood sugar at home, a little finger stick. Here's mine. Here's my uric acid monitor. And there is my most recent level, 4.7. A finger stick. And I do this, it's not something you have to do all the time. You do it every 2 weeks, every 4 weeks. It's not going to change as readily unless you make changes in your diet. But it's really, uric acid now joins ranks with blood pressure and blood sugar and BMI as being a powerful metric as it relates to our metabolic health.
In preparation for my conversation with you, I was reviewing, of course, being a neurologist, I figured we might be talking about Alzheimer's, brain health, and uric acid. And it does seem to be that there are some reports that AMPD, so we were talking before about that bifurcation
Exactly right.
in the pathway, AMPD levels are elevated in the brains of some Alzheimer's patients, which is very...
Oh, no, really? It's really quite pervasive.
Yes. Yeah. So I thought that was an interesting observation. And of course, we know that, and you talked about this in the book about this type 3 diabetes, which you were just mentioning, this sort of insulin resistance in the brain. I guess my question, and this might just be my own lack of understanding, which is why I love podcasts like this, because I get to ask the experts. But does the brain use fructose? Do we have the fructokinase and the whole pathway that all exists in the brain as well? And I know that
Yes,
that may
we
be a
do.
silly
And
question.
That's really a relatively new understanding that the brain not only utilizes fructose, but actually the polyol pathway, the production of fructose in the brain is, the brain has the ability to do that. And beyond that, one very recent study demonstrated that in Alzheimer's patients, fructose and its precursor, which is sorbitol, levels are at least 4 and perhaps 5-fold increased in comparison to non-Alzheimer's brains. So doesn't that explain a whole heck of a lot? And yes, to be sure, this AMP deaminase pathway is dramatically upregulated in the Alzheimer's brain. So there's so much understanding that we're getting now that we didn't have before. And the reason it becomes so exciting because these are going to be new tools for us. That then this metabolism of fructose, because of the downstream issues with increasing inflammation, increasing oxidative stress, and therefore damaging mitochondria, which is, Alzheimer's is ultimately a energy failure in the brain, that this can be perhaps in the future inhibited as we target the enzyme fructokinase. So there is in development right now by major pharmaceutical companies the idea of inhibiting fructokinase. Why would that be incredibly valuable? Well, first, because the laboratory studies on animals show that you can load them up with all the fructose you want. If you inhibit fructokinase, they don't develop the metabolic issues. That even when we look at animal models of non-alcoholic fatty liver disease, load them up with fructose, they don't get non-alcoholic fatty liver disease if you inhibit the metabolism by inhibiting that enzyme, fructokinase. But here's even more exciting information. That if you take laboratory animals, rodents, and you give them alcohol, which would normally produce this alcohol now related fatty liver disease, but you block the fructokinase, they don't develop fatty liver disease even when they're getting alcohol. And what does that tell us? It tells us that the way that alcohol, at least in laboratory animals, produces fatty liver disease is via the increased production of fructose and then the metabolism of fructose. Wow, that's pretty exciting. So, the idea that fructokinase inhibiting drugs are being developed is playing upon this science. And we know, for example, that there are a very small number of people who have an inherited enzyme defect. They don't have fructokinase. They have inherited fructoseuria, where they just, whatever fructose they consume, they basically excrete in their urine. And they can eat and drink all the fructose they want. They can drink sodas day in and day out, and they don't get fatty liver disease. They don't get the metabolic issues. They don't get fat. They can just eat fructose all day long. Now, I'm sure there is some downside, but it does tend to solidify our understanding of what that metabolic pathway is doing in terms of giving us some pretty powerful opportunities in the future. Meanwhile, right now, today, what can you do? 2 things. Reduce fructose consumption dramatically and reduce the activation of our fructose production in our body by limiting our salt consumption, making sure that we're not dehydrated, making sure that we don't get hypoxic at night by having sleep apnea, and watching our alcohol consumption as well.
And you've long been an advocate for the ketogenic diet, of course, for its cognitive, for its brain health, in terms of improving brain capacity and, brain health over the long term. One of the things that you discussed in the book, which I thought was really interesting, is that people who initially maybe go on a ketogenic diet, if they are watching their uric acid levels, that we may see this transient increase in UA levels. But you had in the book, you sort of counsel people to sort of stay the course. How do you reconcile this discrepancy between going on a ketogenic diet and seeing this, elevation, at least transiently, in uric acid levels, and what is the expectation over the long term?
Sure. So why might that be? In our past, when we became ketogenic, why did that happen? We were fasting. Right? Couldn't find food. We started burning. We burned through our glycogen in a day, and now we're burning our body fat as a survival mechanism. And so why would then that be a great time to activate uric acid? Because we don't have food, and we need to do everything we can to ramp down our metabolism, make sure we keep our food resources, our caloric resources, if you will. So that all makes very good sense. There are upsides of ketogenic diet that you've talked about extensively over the years, and then in terms of improving insulin sensitivity and reducing inflammation, even in terms of targeting certain methylation epigenetic pathways that are designed to keep us healthy. But that said, the point is well taken that we should expect uric acid levels to go up when we are fasting or otherwise on a ketogenic diet. But the net benefit at the end of the day is positive, because once you resume regular eating, that your uric acid levels are going to be exactly where they were before or slightly lower. Lower now because you've really improved other aspects of your metabolic pathways that have a bearing on uric acid production. So it shouldn't be a surprise, though, that being in ketosis is going to translate and bump up the uric acid. It isn't dramatic, but I wanted to put that in the book so that people who are getting into ketosis from time to time, which I think is a really valuable thing, or fasting from time to time, don't get excited when the uric acid actually goes up. Oh, I'm going on the ketogenic diet. I heard it was so wonderful, but look at my uric acid levels. It's a good thing. One step back, two steps forward. But I'm glad you brought that up.
Yeah, and I think that this is why a low carbohydrate or a ketogenic diet is so valuable for individuals who are metabolically ill. And it was, kind of piggybacking on what you had just said around, if an individual cuts out sugar, let's say, but they continue to consume carbohydrates and they've already activated this aldose reductase, they're still going to be producing that fructose from excess glucose. Like they're still going to be converting the glucose to the fructose via this carbohydrate consumption. So I think that it's so valuable to even, and I've talked about this, and I know I've been on your podcast talking about, the ketogenic diet for women. I think that this pulsatile phasic, when we are sometimes in ketosis and sometimes not, it's like you sort of pull it back, you get into ketosis, you're using ketones as this, mitochondrial uncoupler and epigenetic signaler. But then you also have times where you're not, so that we can, maintain insulin sensitivity, as you said, and continue to sort of keep things in the best sort of homeostatic balance that we can.
Well, the notion of cycling you brought out in your book, and I thought that's really valuable. That's really extremely valuable. And that clearly would emulate what our paleo ancestors would have experienced: feast and famine. The notion of always locking into ketosis. And yet there are interventional trials where that is done for a period of time. We've seen one in Parkinson's and Alzheimer's. Matthew Phillips in New Zealand is doing those, has done those, published them. But I think, as you well point out, this metabolic flexibility is really seemingly the goal today, and with good reason. But, again, when we look at it through the lens of how is it signaling this survival pathway, it makes total sense. You're in ketosis, your body says, whoa, we're burning fat, there's no food, bump up the uric acid, that'll specifically slow metabolism. How does it do that? It does so by the increased oxidative stress from the uric acid, directly increases oxidative stress intracellularly, and that affects mitochondrial function. Therefore, metabolism is compromised. And it threatens the viability of mitochondria and the functionality of mitochondria. One recent study carried out by a Dr. Richard Johnson, one of the investigators at University of Colorado, put people on an extremely low fructose and low sodium diet and demonstrated in the mitochondria count of white blood cells an increase of 1,000% after several weeks of being on that diet in humans. So, what a great tool to upregulate mitochondrial biogenesis. I mean, there are other things that we've talked about before, looking at the mTOR pathway, et cetera, looking at the notion of getting rid of bad or defective mitochondria through enhancing mitophagy. But what an interesting approach then to increasing the pure mitochondrial count via reducing oxidative stress, because we're going to turn off that polyol pathway. We're not going to make fructose, and by reducing the sodium, and we are going to reduce the consumption dramatically of fructose. So we're getting rid of the fructose we take in, reducing the fructose that we make. But I think it's sticking in my mind, this notion that in Alzheimer's brains, there's this dramatic uptick in the production of fructose from glucose, and that glucose levels in the brain are elevated in the Alzheimer's brain in comparison to non-Alzheimer's patients as well. And that forces this whole polyol pathway to make then this fructose. So, we thought, oh gosh, there's a problem with getting glucose into the brain in Alzheimer's because the transporter mechanisms in the blood-brain barrier, insulin dependent, might not work as well. But the reality is, in many parts of the brain, the glucose levels are much higher, but it's a question of then the utilization of that glucose. And this insulin resistance is exacerbated as the fructose levels climb. Gosh, it's you and I could have had this conversation a couple of years ago, and there would have been a lot of holes in it. But it's really coming together. It's like finding the corner pieces on a jigsaw puzzle. You go, whoa! I just connected the barn with the river, and this is a great moment.
As a puzzler, I really appreciate that, because I often do puzzles. That's my sort of way to uncheck from the world, to
it's
get
great.
into
My wife will be working on one part and I'll work on another part. And then when they fit together, we go, oh my gosh, that's half the puzzle right there.
I made my husband and I did one over the holidays. It was just the musculoskeletal system. So there's just like the muscles on one side, and then it was the bones on the other. So you can imagine all the same colors, right? So the femur looks exactly like the humerus. Anyway, all right. So let's get back to uric acid. What are some dietary edits or some supplemental hacks? I don't like the word hack. I love Dave Asprey, but that's just one of my words that, it sort of means shortcut. But anyway, what are some of the simple dietary edits that we can make to employ to lower our uric acid levels?
Well, let's call them tools, because that's a term I use in the book. And first of all, it's what do we take out, and then what do we put in? And it doesn't have to be in any particular order. What do we take out? Salt, fructose. Those are the easy things. Does that mean don't eat fruit? Not at all. As it turns out, fruit consumption is associated with a slightly lower uric acid. Now, that might sound challenging because fruit contains fruit sugar, in other words, fructose. But the reality is it actually doesn't contain a whole heck of a lot. Even an apple, even the monstrous apples that we see these days, maybe 5, maybe 10 grams of fructose. That seems like a lot, but that doesn't come anywhere near the amount of sugar in a glass of fruit juice, for example, or a soda. The other thing is it's the context. It's delivered with dietary fiber that slows the fructose consumption, so the liver doesn't get overwhelmed and can process that 4 to 5 grams in a short period of time. It's also delivered with vitamin C that aids in uric acid excretion. And it's also delivered with certain bioflavonoids like quercetin that actually targets the enzyme that creates uric acid called xanthine oxidase. So xanthine oxidase reduces uric acid production. It's how the gout drug allopurinol works. Now, we can really effectively lower uric acid by eating fruit, but we can also add in taking quercetin as a supplement, 500 milligrams per day. One study published in the British Journal of Nutrition, 22 males, young men with elevation of uric acid took 500 milligrams a day of quercetin, and they dropped their uric acid 8% in 2 weeks. So it's a really powerful intervention. So on the front end, we want to look at purines, organ meats, game meats, shellfish like mussels and scallops. We want to limit alcohol consumption, recognizing that hard liquor is associated with increased uric acid, that wine in men has really no effect, but wine consumption in women is actually associated with a lower uric acid. So that's kind of on the table.
Red or white?
Pardon me?
Red or white?
Definitely want to go with red. Why? Because that is made with the skins. You're going to get more of the polyphenols. But beer consumption is associated with a dramatic increased risk of elevation of uric acid in both men and women. Why might that be? Well, beer contains alcohol, but beer contains a lot of purines because it's made from brewer's yeast. So you're getting a double hit. In Japan, frankly, Japan is way ahead of North America in terms of their understanding of this whole discussion that we are having. They are now, they're doing two things I think are interesting. They're treating hypertension by lowering uric acid, and they're also marketing zero purine beer. I mean, we've heard of non-alcoholic beer for many years, but now there are no purine beers being sold in I think Canada and the United States, but certainly developed and marketed in Japan. So just something to think about. So it's not alcohol globally, it's alcohol specifically in terms of what you might have. I want to just say, as it relates to the upside, which is you might find this to be good news, coffee helps lower uric acid. Yes. So you can feel good about having coffee. That's a good thing. Now, as it relates to what the diet should look like, a lot of dietary fiber, and a call out to the keto people. Keto is great as it relates to not consuming carbs, but keep in mind that dietary fiber is carbohydrate. So you don't want to eliminate dietary fiber, though it's a carb. Really important that we have carbs on board. It slows the absorption of fruit sugar, of fructose, but also really important to nurture the microbiome. We'll talk about that in relation to uric acid if we have time. So dietary fiber, really important. But one other thing is that these fiber-rich vegetables contain a lot of these bioflavonoids, natural sources of things like luteolin and quercetin that specifically target that xanthine oxidase enzyme that when it's targeted will slow the production of uric acid. And again, another resource for vitamin C to help with its excretion. And it's an interesting story that our bodies don't make vitamin C because, and therefore that's another reason to eat fruit, but we don't make vitamin C. One of the ideas being that, and interestingly, traditionally, when fruit is ripe, the vitamin C content is the lowest. And therefore, was there ever an advantage to not having the enzyme pathways to make vitamin C and to not really have a lot of vitamin C? Well, you certainly don't want it so low that you get scurvy. But having said that, what is vitamin C? It's an antioxidant, and oxidative stress signals through an enzyme called cis-aconitase in the Krebs cycle to actually increase fat production. So that might be why we lost 10 million years ago the ability to make vitamin C. So again, looking at it through the context of how might that have been an advantage for our ancestors, who knows? Now then, on the upside, then a diet that's really rich in plant-based foods. If you're going to eat meat, plenty of foods that you can eat, but in moderation. So let's reduce, especially those purine-rich foods like liver and kidney and scallops and mussels and seafood, shellfish rather. Salmon is a good choice as compared to things like sardines and anchovies, smaller fish, more dense cells, higher levels ultimately of purines. But again, it may be that you get away with it, and that's okay if your uric acid level is where you want it. If you're taking the 500 milligrams of quercetin a day, 100 milligrams of luteolin, 500 milligrams of vitamin C, all with the idea in mind to lower uric acid. Those have been approaches used in gout for a long, long time, in addition to the consumption of something called tart cherries. Tart cherries contain that suite of bioflavonoids that directly lower uric acid. Tart cherries have been used for gout treatment for decades and decades because they look, what is the O in drop acid? It's a cherry, right? You see it falling. And we wanted to connote the fact that certain foods will lower your uric acid, while we're knocking hardly on things that contain a lot of fructose. Fruit juice, steer clear of that. Fructose in so many of its disguised names that appear in in various products, cane sugar or fruit juice concentrate. Oh, that sounds great. I'm getting all the benefits of fruit juice and fruit juice concentrate. Sign me up for that one. Well, no, what's basically concentrated is the fructose, the fruit sugar. Fructose is sweeter than glucose. It's cheaper than glucose. Hence, the production of high fructose corn syrup, which just exploded in the 1970s, although the actual technology was, I think, developed in 1957 by a Dr. Marshall at University of Oklahoma. We've known about it for a long time. And truthfully, there have been a lot of politics involved here in terms of why we decided to get our sugar from corn, mostly, as opposed from cane sugar, which came from other countries, though some from Florida, but from Cuba. Think about when this all happened, so there's politics involved and economics involved. But ultimately, it's about food manufacturers getting more bang for the buck, cheaper ingredients, sweeter foods using this high fructose corn syrup.
So I think the general rule of thumb, if I can summarize, certainly open to expanding on it, is you want to think about the velocity at which this is going to hit the liver. Like you've talked about fruit, like the tart cherries and, other whole foods like an apple, but the apple juice, let's say, or cherry juice derivative is going to hit the liver much faster with a much higher concentration of fructose, which is going to start that de novo lipogenesis. And then the whole uric acid pathway that we discussed. And the same is true, I think, for beer as well, like very dense, lots of cells, but it's also going to hit the liver because it's liquid sugar. It is going to hit the liver much faster than, I don't know what the solid equivalent of beer might be, but, we want to be thinking about, tart cherries and apples versus apple juice and cherry juice.
Exactly. I mean, so now there is real good understanding of what's causing the beer belly. You're targeting that pathway twice. You're targeting with the alcohol and you're targeting it with the purines. And that's bumping up the uric acid. And you look at the uric acid level in individuals who have a beer belly or who have high BMIs, and they are across the board elevated. You look at uric acid levels and see how profoundly it correlates with type 2 diabetes and hypertension. You see it across the board in the issues related to dysfunctional metabolism. So, we look at at where it's coming from now. And so again, the degree of satisfaction that I get is finally the jigsaw puzzle. It really answers an awful lot of questions. And again, the perspective of the historical advantage that it offered us during times unlike today, when we didn't stimulate these pathways with alcohol and fructose. The alcohol part of the story, I think, is really interesting. And we developed about 10 million years ago the ability to metabolize alcohol and therefore make fat. The ability to metabolize alcohol was an advantage because it allowed us, our primate ancestors at the time, allowed them to eat during times of food scarcity, dare I say, rotten fruit. And what does rotten fruit mean? It's already rotting on the ground and it's fermenting. The sugars are fermenting and forming alcohol, and it's not toxic once we develop the ability enzymatically to break it down. So we experienced 10 million years ago about a 60-fold improvement in our ability to metabolize alcohol. Again, because it opened up the door to having the ability to consume that without downside. Wouldn't get as drunk because we could metabolize the alcohol, be less threatening for I say us, but our primate ancestors. So it's really just so interesting to look at this. But I think today, when we are faced with the notion that here in North America, 1 in 3 adults is obese, not just overweight, but obese, and that by the year 2030, which is sometime in the distant future, right? 8 years from now, that it'll be 50%. 50% of adults in North America obese. And again, that's just not having a few extra pounds. That's clinical obesity, half. It's breathtaking, especially not just from the issues related to it, but what are the consequences of that obesity in terms of risk for Alzheimer's, diabetes, coronary artery disease, cancer, you name it. There are so many issues, and specifically the cancers, the breast cancer, colon cancer, and pancreatic cancer. Those are the ones most related to that change in metabolism. And it's a consequence of choice. It's a consequence of, on the one hand, what's being done to our food. I'm sure you had a wonderful conversation with Dr. Lustig about that. And B, the choices that we could make or should make, but we might not even now be able to make because we've been so overridden and captivated by what's going on to influence us.
Any medications that you wanted to mention in terms of to be aware of in terms of ones that might be potentially also elevating uric acid levels? I know we've been talking about obesity, but of course the tendency for someone who is sick, obese, who has high blood pressure, who has all of these other conditions that they're dealing with, there tends to be an increase in medication use. So do you want to touch on some of the medications that might elevate uric acid levels?
And there are actually quite a few on the list. And perhaps the most widely used is aspirin. Aspirin is known, though interestingly, aspirin is used for gout treatment and yet is associated with increased uric acid. The next one is actually quite interesting. Is sildenafil, which is Viagra. So Viagra directly raises uric acid. And how does Viagra work? Viagra is a drug given for erectile dysfunction because it improves the function of nitric oxide, allowing the blood vessels to dilate, therefore helping with erectile dysfunction. And yet at the same time, it's raising uric acid, and uric acid works against that whole mechanism, compromising the function of nitric oxide. It may explain why there is a 38% increased risk of erectile dysfunction in men who have higher levels of uric acid. Another drug is theophylline, possibly being used more these days, a drug for lung issues used in things like asthma. But there may be some usage of theophylline in people who are having breathing issues as a consequence of COVID. Another group of drugs that is widely used are what are called the proton pump inhibitors. These are the so-called over-the-counter acid-blocking drugs that incredibly don't require a prescription, used by 13 million Americans. And what's the downside? The downside is they are associated with dramatically increasing uric acid. Another class of drugs that interestingly is used for people with high blood pressure are the beta blockers. These are drugs like metoprolol and Inderal that are used for people with high blood pressure and certain other problems, cardiac dysrhythmia. But at the same time, will raise uric acid. So you're kind of working against yourself. And it's relatively new information that there's so it was thought, well, if you don't have gout, by all means, take all the beta blocker you want, the theophylline, the aspirin, the Viagra, the proton pump inhibiting drugs, fine, because if you don't have gout, what's the big whoop here, right? But now that we understand the role of uric acid in the very diseases that these drugs are targeting, we should be rethinking what we're doing. And if a person requires a medication, great. But let's look at our choices through the lens of, does that drug increase or not uric acid? Because if it does, then you're working against yourself.
And we've mentioned a couple of times that, every point over 7, we have 8 to 13% increase in all-cause mortality. What is your ideal uric acid levels? Do you have an optimal range? I know that many labs, they don't start really, warning the bell unless it's 7 or above. Is there a range that you would like to see, ideally a functional range?
I think it really not a range. We're looking to have the uric acid level at 5.5 or below. And your point is well taken, that if you go to a lab or go to a doctor and she tells you, well, you're okay because your uric acid level is 6.9, understand there's two things wrong with that. First, that's telling you that you're in the normal range. And Stephanie, none of the people that you are involved with wants to be normal. They want to be optimal, right? So let's get rid of that whole notion of in the normal. Normal means average. And these days, average is just not the metric that we want to strive for.
Yeah.
And beyond that, the number 7 is derived for those people in terms of their gout risk. And it actually comes from the understanding that it's really above 7 where the very crystallization, where uric acid begins to precipitate out in the extracellular space, and then starts to form these crystals that form, as you mentioned, in the great toe, but also form in the blood vessels of the heart and even in the prostate gland. So it's above 7 that sort of starts to happen in some people. I mean, it depends on a lot of things. It depends on pH, depends on hydration, lots of different things. But again, those values are derived in relation to gout. And as I mentioned when we started, this is not your grandfather's uric acid anymore. In other words, we're well away from the notion that uric acid relates to gout or kidney stones, end of story. There is this idea of I mentioned in the book, called asymptomatic hyperuricemia, meaning you have elevated uric acid, but there are no symptoms, meaning you don't have gout and you don't have kidney stones. Well, asymptomatic hyperuricemia is associated with obesity, diabetes, dyslipidemia, meaning having problems with your good and bad cholesterol. So there's nothing asymptomatic about it. It's just we didn't recognize that before, but now that we do, we've got to take it a lot more seriously. I mean, you have a uric acid level of 8, but you don't have gout in your toe. Therefore, you'll be on your way. And, there's a lot more implication of this now than we ever understood. The upside is we've got a great new tool that we can leverage to help people regain their metabolic health.
Well, I know I'm just looking at the time, and unbelievably, we're pushing up on 90 minutes of conversation. I feel every time you come onto the show, there's so much more I want to talk to you with, about and with, and I always value your time. So I wanted to congratulate you on the book. It is absolutely incredible. All of your books are incredible. This one was very, very well done. You've explained very complicated pathways.
It is a bit complicated, I know, and that's always the challenge: is how can we phrase this so that people can get their arms around it? Because I think once you get your arms around, the fact that these were survival mechanisms, the fact that we can turn on the production of fructose, and you don't have to memorize the enzymes, whatever, but just, hey, I understand now why eating a lot of salt is not necessarily in my interest, because it can lead to obesity. You don't even have to get the full connection, but just the relationship between salt and weight gain, salt and risk for diabetes, for example. And certainly people have known about salt and hypertension for a long time, but that's the challenge in writing these kinds of books, is to make it understandable, at least so that you can walk away and have some tools to bring about better health. And really what I hope for is extraordinary health for all the people that we're dealing with.
Well, you've done a beautiful job of explaining it in a way that I think many people can understand, as well as giving nerds like me enough information to salivate over and to go down a geeky magic carpet ride in PubMed. So I just wanted to give you some kudos on the book.
And thank you so much, Stephanie.
You're welcome. And we're going to be releasing this the week that your book comes out. So just a plug for, I know that you have some, I think there's a sugar download that you may have on drperlmutter.com. Do you want to tell people where they can find the book, and then any bonuses that they might look to pursue?
So the book's available everywhere, all the online retailers and all of the bookstores around. If you want to learn more about the book, it's called Drop Acid, and oddly enough, the URL online is dropacidbook.com. That'd be a great place to start, or just visit drperlmutter.com, drperlmutter.com. But on dropacidbook.com are all the things that you're referring to, the pre-order gifts that are going out, and a lot of the reviews of the book that I've been so grateful to get, and just the fact that people have recognized that this is yet another tool that we can empower ourselves with in the face of the direct conflict to our health that is being offered up by people who don't have us, our health at best interest. A great book, another book to read would be Metabolical by Dr. Robert Lustig. And he really calls out, what's going on behind the scenes that makes us ultimately eat more fructose, raise our uric acid level, and therefore threaten our health. So it's very nice that so many people are involved in calling this out. And, it's all about, seeing things as they are, not saying, but really making them better. We can ask why but we can really do our best to make them better. So there you go.
Wonderful. Well, I will make sure to put all of those links in the show notes. And maybe the third guest that I need to have on the show is Rick Johnson, just to complete the trifecta of Perlmutter,
I will
Lustig.
help you make that happen. He's a wonderful, wonderful guest. And as you probably noted, I dedicated my book to him.
Yes, I saw.
He has done so much research. And he's a great guy. He's a terrific guy. So we've become great friends. We've never personally met vis-a-vis COVID, but we will, I'm sure, one day.
Wonderful, wonderful. Thank you again, Doc.
Thank you. Good to see you.
If you enjoyed that conversation and you want to learn more about hormones, check out this video right here.
There was a recently published study challenging the validity of any of the conclusions from Blue Zone diets and actually pointing the finger at poor record keeping in these countries